Here is a combined summary of the 2 pages. This research paper proposes a novel approach to robust fast adaptation in metalearning, addressing the issue of task distribution shifts that can weaken the generalization capability of metal learners. The authors introduce an explicit generative modeling of task distributions, which can be interpreted as a Stackelberg game. This approach not only uncovers task structures during problem solving but also theoretically increases adaptation robustness in worst cases. The authors highlight the limitations of existing metalearning methods, which often adopt handcrafted or simple prior task distributions, leading to catastrophic failures in real-world scenarios when distribution shifts occur. They propose a solution that involves generating task distribution shifts at a certain level and modeling the robustness issue with a Stackelberg game. The approach utilizes normalizing flows to parameterize the distribution adversary and the metal learner for fast adaptation in the presence of distribution shifts. The optimization process can be translated as fast adaptation robustification through adversarially explicit task distribution generation. The authors also provide a theoretical analysis of the solution concept, using alternating stochastic gradient descent to approximately solve the game and performing convergence and generalization analysis under certain conditions. The paper reviews related work in metalearning and adaptation robustness, discussing various families of metalearning methods, including optimization-based, deep metrics, and context-based methods. It also highlights previous work on task distribution studies in metalearning, including task augmentation, task relatedness, and neural task samplers. The authors define the notation and recap fundamentals in metalearning, including the risk function and the metadata set. They also provide a problem statement, revisiting the standard metalearning optimization objective and highlighting the need for robust fast adaptation in the presence of task distribution shifts. Overall, this research proposes a novel approach to robust fast adaptation in metalearning, addressing a critical issue in the field. The approach has practical implications for dealing with task distribution shifts in metalearning and contributes to theoretical insights in the field. The research paper discusses a novel approach to metalearning by introducing a game-theoretic framework. It focuses on robust fast adaptation from adversarial task distribution generation. The authors propose a Stackelberg game between a meta-learner and a distribution adversary, where the meta-learner aims to learn robust strategies, and the distribution adversary attempts to generate task distributions that challenge the meta-learner's adaptation. The optimization objective is formulated as a min-max problem, ensuring the meta-learner's robustness against potential task distribution shifts. The paper also utilizes normalizing flows for generating task distributions, which offers tractability and flexibility. The authors provide detailed examples of how this framework can be applied to MAML and CNP, 2 popular metalearning algorithms. The summary highlights the significance of the proposed approach in enhancing metalearning's robustness against distribution shifts, making it more adaptable to real-world scenarios. In this research paper, the authors propose a novel approach to metalearning, which involves recasting the task of adversarially robust metalearning into a Stackelberg game. The paper discusses the game's equilibrium and its theoretical properties in generating task distributions. The authors also present experimental results and compare their approach, ARMAML, with other baselines such as vanilla MAML, DROMAML, TRMAML, and DRMAML. The paper first introduces the concept of a Stackelberg game and its application in adversarially robust metalearning. The authors then discuss the optimization objective and strategies for finding equilibrium, including the use of stochastic gradients and variance reduction techniques. They also provide a theoretical analysis of the convergence guarantee and generalization bound with the distribution adversary. The experimental section evaluates the performance of ARMAML on various benchmarks, including synthetic regression, system identification, and meta-reinforcement learning. The results show that ARMAML mostly outperforms other baselines in the adversarial distribution and sometimes boosts average performance on the initial distribution. The authors also analyze the role of task distributions in metalearning and discuss the implications of their findings. Overall, this paper presents a new perspective on metalearning by leveraging game theory and generative modeling. It provides insights into the theoretical properties of adversarially robust metalearning and demonstrates the effectiveness of the proposed approach through experimental results. This research focuses on robust fast adaptation from adversarially explicit task distribution generation. The authors evaluate the performance of various metalearning methods, including MAML, TRMAML, DRMAML, DROMAML, and ARMAML, on several benchmarks, such as sinusoid regression, acrobat system identification, and pendulum system identification. The results, presented in Table 1, demonstrate that ARMAML achieves the best performance in terms of average mean square errors and conditional value at risk, CVAR, with alpha equals 0.5. The authors also investigate the robustness of metal earners to random perturbations and distribution shifts. Figures 47 illustrate that ARMAML exhibits superior performance in terms of CVAR and average returns in point robot navigation and ant-pos tasks. Moreover, ARMAML demonstrates robustness to random noise in the support set, as shown in Figure 8. The authors analyze the learned task distribution adversary, visualizing the adversarial task probability density in Figure 9. The results reveal that the approach can discover explicit task structures, and the learned patterns are similar across different initial task distributions. Additionally, the authors investigate the impact of shift distribution constraints and the compatibility of ARMAML with other metalearning methods. The research contributes to the understanding of robust fast adaptation and provides insights into the development of more robust and adaptable metalearning methods. The proposed approach has the potential to improve the performance of machine learning models in real-world applications, where data distributions may shift or exhibit uncertainty. This research paper introduces a novel approach to fast adaptation in metalearning, specifically focusing on robustness to adversarially generated task distributions. The authors propose a method that leverages conditional neural processes to model task distributions, enabling the discovery of interpretable task structures and optimization. The approach is evaluated on the sinusoid regression task, demonstrating improved adaptation robustness in constrained distribution shifts. The paper begins by highlighting the limitations of existing metalearning methods, which often failed to generalize well to unseen tasks. The authors argue that this is due to the lack of robustness to distribution shifts, and propose a solution that involves generating tasks using a conditional neural process. This allows the model to learn a robust representation of tasks that can be adapted to new, unseen tasks. The authors evaluate their approach on the sinusoid regression task, comparing it to existing methods such as CNP, TRCNP, DRCNP, and DROCNP. The results show that their approach, ARCNP, achieves the best performance in terms of mean squared error, demonstrating improved adaptation robustness in constrained distribution shifts. The paper also discusses the limitations of the current approach, including the reliance on task identifiers, which can be inaccessible in certain cases, and the approximate nature of the game solution, leading to suboptimality in optimization. Future work is suggested to overcome these limitations and facilitate robust adaptation in applications. The references section provides a comprehensive overview of the related work in metalearning, including papers on gradient-based metalearning, neural processes, and distribution-ally robust optimization. The authors acknowledge the contributions of previous researchers in the field, highlighting the importance of building upon existing knowledge to advance the state-of-the-art in metalearning. This paper presents a novel approach to task-robust metalearning under distribution shift constraints. The authors leverage a game-theoretic framework, specifically the two-player Stackelberg game, to generate task distributions within an adversarial setting. This approach allows for the exploration of task structure discovery under risk minimization principles. The proposed method, ARMAML, is an extension of the model-agnostic meta-learning (MAML) algorithm. It utilizes normalizing flows to model the task distribution, enabling the discovery of complex task structures. The authors also introduce the ARCNP, which replaces the MAML inner loop with conditional neural processes for task inference. The paper provides a comprehensive theoretical understanding of generating task distributions using the Stackelberg game. It discusses the existence of Stackelberg equilibrium, convergence guarantee, and convergence properties. Additionally, the authors present a generalization bound and formal adversarial generalization bounds. The experimental section showcases the effectiveness of ARM-AML and ARCNP on various benchmarks. The results demonstrate improved robustness in the presence of distribution shifts. Further investigations include task structure analysis and other related work summaries. In the supplementary materials, the authors provide detailed guidelines for implementing ARM-AML and ARCNP. This includes pseudocode, player order in decision-making, benefits of explicit generative modeling, and setup of base distributions. Furthermore, the supplementary materials cover additional experimental results, platforms, and computational tools used in the study. Overall, this paper contributes to the field of metalearning by introducing a new approach that leverages game theory and normalizing flows to improve task robustness under distribution shifts. The proposed methods and theoretical analyses offer insights into the development of more robust and adaptable machine learning models. The research paper discusses an adversarially task robust CNP algorithm, focusing on robust fast adaptation in metalearning. It introduces a novel approach by incorporating an explicit generative modeling of the task distribution, enabling the metal learner to converge to a distribution that focuses on more challenging scenarios. The algorithm involves a leader-follower game, where the leader updates the model parameters, and the follower updates the task distribution. The order of decision-making between the leader and follower is crucial, as it influences the solution concept. The paper also compares their method with existing SOTA and typical SOTA methods, highlighting the benefits of their approach in terms of robustness and adaptability. Additionally, it discusses related work in robust fast adaptation, including distribution ally robust optimization and tail risk minimization, emphasizing the importance of capturing the differentiation information from task identifiers to uncover the task structure. The summary concludes by highlighting the significance of their method in enhancing fast adaptation robustness when confronted with task distribution shifts. The paper discusses stochastic gradient estimates for adversarial generative models, focusing on the exact computation of task likelihoods. It introduces a novel optimization objective that includes a KL divergence term to ensure the generated task distribution remains within a tolerant region of the initial task distribution. This setup encourages exploration of crucial tasks while preventing mode collapse. The optimization process is framed as a Stackelberg game, where the metal earner and the distribution adversary make decisions iteratively. The paper proves the existence of a global Stackelberg equilibrium and guarantees linear convergence to this equilibrium. The stochastic alternating gradient descent ascent is used to solve this adversarial task robust metalearning problem. Here is a combined summary of pages 17 and 18 of the research paper. The authors investigate the convergence properties of an alternating gradient descent ascent (GDA) method for solving an adaptively robust metalearning problem. They linearize the utility function around the Stackelberg equilibrium, which leads to a new form of learning dynamics. By rewriting the matrices involved, they derive an upper bound for the norm of the updated parameters. This bound is then used to prove two convergence properties of the iteration sequence. The first property states that the sequence is Cauchy, implying that it converges to a fixed point. The second property shows that the sequence converges to the local Stackelberg equilibrium with a linear rate of square root delta. The authors also discuss the importance of the weighting trick in generalization bounds for reweighted risk and provide a lemma from previous work on this topic. The lemma states that the generalization bound for reweighted risk is controlled by the pseudo-dimension of the hypothesis space and the range of the importance weights. The authors then provide a detailed explanation of the terms involved in the lemma, including the expected risk of interest and the empirical risk. The analysis is performed in the context of generative task distributions, where the task distribution is adaptive and learnable. The authors aim to provide a generalization bound for the reweighted risk, which is challenging to analyze directly. Instead, they exploit the importance of the weighting trick to derive the bound. The formal adversarial generalization bounds are derived, focusing on the uniform distribution as the base distribution. The equation for omega, tau 0 k, is presented, involving the logarithmic difference between the task probability density and the initial task distribution. The bound is then used to formulate the generalization bound of meta-learners under the learned adversarial task distribution. Theorem 2 provides the generalization bound with the distribution adversary, considering the pre-trained normalizing flows and the pseudo-dimension. This framework is applied to various benchmarks, including sinusoid regression, acrobat system, and pendulum system, showcasing the versatility of the approach. The entropy of task distributions is analyzed, highlighting the tractable likelihood of the generated task distributions. Experimental setups and implementation details are provided for each benchmark, demonstrating the practical application of the theoretical framework. The research focuses on meta-learning continuous control, specifically in reinforcement learning, where the goal is to guide robots to move towards a target goal step by step. For this, the authors use a random policy as the controller to interact with the environment and collect transition samples. They also employ a neural network model for the regression experiments with adaptively robust MAML. The model consists of a distribution adversary and a meta-learner. The distribution adversary module is designed to transform random variables, and the meta-learner module implements the MLP for the implementation of MAML. The authors detail the implementation of these modules in PyTorch, highlighting the use of normalizing flows and the specific configurations for the robot navigation task. The summary covers the key components, methodologies, and technical details from both pages, providing a comprehensive overview of the research. The paper presents a meta-learning approach that incorporates a distribution adversary to improve the robustness of meta-learners against task distribution shifts. The distribution adversary is implemented using normalizing flows, specifically a two-layer planar flow with leaky ReLU activation functions. The last layer employs min-max normalization to transform the initial distribution. The meta-learner architecture is based on a multi-layer perceptron, MLP, with 3 hidden layers, each consisting of 128 hidden units, and rectified linear unit, ReLU, activation functions. The inner loop utilizes stochastic gradient descent, SGD, for fast adaptation, while the outer loop employs the atom optimizer to update the initial parameters. In the sinusoid regression and system identification benchmarks, the Lagrange multiplier lambda is set to 0.2 to cover most shifted task distributions. The learning rate for both the inner and outer loops is set to 1e3. For the continuous control benchmark, lambda is set to 0.0, and MAML serves as the underlying neural network architecture. The agent's reward is the negative squared distance to the goal, and the agents are trained for one gradient update using policy gradient with generalized advantage estimation and trust region policy optimization, TRPO, in the outer loop update. The paper also presents additional experimental results on tail risk robustness across various confidence levels alpha for sinusoid regression and acrobat system identification. The results show that ARMAML exhibits a more significant performance gain in the adversarial distribution than in the initial distribution. Furthermore, the paper explores the impacts of shift distribution constraints by varying the Lagrange multipliers lambda and includes the learned task structures and metatesting results. The implementation of the distribution adversary and meta-learner uses PyTorch as the deep learning toolkit, and the experiments are run on NVIDIA 1080T GPUs. The paper also provides a detailed description of the neural architectures and optimization methods used in the experiments. The supplementary materials detail the work in progress, focusing on various benchmarks and distributions. The first part discusses the CVAR alpha MSS with different confidence levels alpha for the Acrobat U and Acrobat N initial distributions, as well as adversarial distributions. The plots report meta-testing CVAR alpha MSS with standard error bars. Additionally, Table 5 presents the entropy of initial and adversarial distributions under different lambda values for the sinusoid U and sinusoid N benchmarks.